So thank you very much for the organizers for organizing such a great conference and giving me opportunity to talk a bit. So I'm just a doctorate student before I studied physics, but the category theory I studied just for a few years, so this will be not so rather elementary topics, and a lot of these are just my thoughts, hypotheses, so I'm very open to your comments and information. So the plan is roughly like this. First, very short introduction. I think I will skip a lot of this because I was thinking maybe there are some people outside of category theory, but here I think almost everybody is familiar with this. Then I will say what are the so-called co-toposes, at least in certain attitude to it by some authors. Then I will make some analysis of this definition because I think this is not the right way to do this dualization. And some further remarks that came to me when I was thinking about this whole stuff and some conclusion. So this I will skip. I just start, we all know this is just standard things. The logic of toposes is known to be intuitionistic logic, of course. Nota bene, Colin pointed out in his book that topos logic coincides with no intuitionistic logic studied before toposes. And of course, the motivations for doing category theory were completely outside of the intuitionistic philosophy, but it happens that the logic is intuitionistic. It plays a great role in some aspects of topos theory, like a lot of things, for example, in existence of infinitesimals in smooth differential geometry. But however, recently there appeared some papers about possibility of dualizing intuitionistic logic into paraconsistent logic in the context of toposes. You don't have to know almost anything about paraconsistent logic. I would just assume it to be a dual for the intuitionistic logic. So, yeah?
Are you talking about propositional logic or higher order logic?
Yeah, so...
because I think Colin was talking about the higher order logic.
Yeah.
The propositional logic
is the same. Yeah, that's true. That's true. So I'm talking here, yesterday also Colin told me some interesting remarks about it. So I will talk about just propositional logic, and I still think this is not the way it should be done, let's say, but this is just it. So you have only to know that this is connected with the reversal of the order in Heyting algebra for the co-Heyting. Yeah, so this is in connection with our subject of the conference. I think if it would be true, and I will say I think this is not the way to do it, but there is a way to do it. I think there is some kind of aspects of paraconsistent logic in topos theory, but if that would be true, this would very strongly extend the potential of topos theory to be used, for example, in physical theories, I guess. Okay, so this is like, I will just shortly give you the definition of the complement-topos. I think this is the idea that the authors have in mind giving this definition. If we take a topos set, a standard one, very standard, and we take an arrow, a global element which takes not a 1 but a 0, from the categorical point of view, I think this is, of course, the same thing. But they say, first of all, it will classify subobjects, of course. It will classify, if we look at it from outside, from the standard set theory, we say it classifies the subobject with the characteristic morphism, with the complement characteristic morphism. So the subset, we go to 0, not to 1, but this is also, it classifies. But this is, I think, the important part, because from the external point of view, from the set theory, we know that 0 is less than 1. We have an order here somehow. Then we will say that the bigger subobject, the smaller its complement characteristic arrow. So then it reverses the order on the complement characteristics arrow. So this is how of course, this paraconsistent and co-Heyting algebras would emerge. Yeah, so this would make this a co-Heyting algebra. Okay, I will just make it more precise in general now. So first, I would like to say a few words about the motivation for co-toposes that these people give. So we know toposes are generalization of topological spaces. For example, you can also consider it as a generalization of set theory also. And now the algebra of open sets of some topological space is the Heyting algebra, of course, which is the semantics for intuitionistic logic. But the topology can be equivalently specified by the family of closed sets. So, and as a matter of fact, they first, Tarski and Kinsey said, considered closure algebras as a sort of algebra of topology. Then it started to be the interior, the open sets. And I learned from, I think it's in MacLean and Merdick book, that the first general explicit definition of a sheave in a space was described in terms of closed sets of that space. So this is the motivation by Morensen. He's from Adelaide, I think. He's one of the guys that put this co-toposes definition. He says, specifying a topological space but its closed sets, what I said, is as natural as specifying it by its open set. So it would seem odd that topos theory should be associated with open sets rather than closed sets. Yet this is what would be the case if open set logic were the natural propositional logic of toposes. At any rate, there should be a simple topological transformation of the theory of toposes, which stands to closed sets and their logic as topos theory does to open sets and intuitionism. So this is their motivation. And the definition of a complement classifier, because a complement-topos, or the co-topos in short, is a category, so it's the same with initial and terminal object, pullbacks, pushouts, exponentiation, and complement classifier. Of course, you can omit the initial and pushouts, as you can deduce this from others, but I just put the definition they have in a book. So everything is the same. So Cartesian closed category, but instead of a subobject classifier, we give a complement classifier, which is absolutely the same definition as a subobject classifier, but we say that the classifying the general generic subobject is false instead of true. It's also, for me, it looked very strange at first. So everything goes the same, but we say there is an arrow, we call it false, that for every monic there's a unique arrow that makes the pullback. So I will comment now on it.
It's not classifying the complement of the monic, it's classifying the monic.
So I think this is what they want to do, but this is what they give a definition. So we start with just a monic.
This is just changing the terminology.
Yeah. So I think they had in mind they want to classify the complements, but they give this definition. So, yeah. Yeah, so roughly part of my presentation is just this. But I was, but I'm happy to see your reaction, because there are some papers, even books, maybe not whole books, but some chapters in books which develop this complement-toposes. And I have strange feelings about this. Okay. Yeah, so this is what they see it partially, because this is one of the people, he wrote a PhD about this also. He writes, examination of the notion of a complement classifier is an external or ex-categorical dualization of logic structures by interpretation of order. Or another author says, complement-toposes are not categorically distinct from standard toposes, but it does not imply that those alternative labelings give rise to the same internal logic. I would say, if only, I mean, that's also not true, but to the same external logic, maybe. Somehow, but internal logic is you have just the structure of arrows. No, whatsoever the names you have, they are just, compositions of them. This is what defines a category. So I will skip it maybe quite fast, because this is what are the consequences if we assume hypothetically that we have a complement classifier. Okay, so of course we define truth now as a complement characteristic morphism of this morphism from 0 to 1, from initial object to terminal object, when you have the logical connectives done in a dual way. So for example, disjunction, they now ask when disjunction is false. So it is false when both sentences are false. So this would be a complement character of this product. As in standard toposes, we say we have truth here, and we say that conjunction is the character of this product, because conjunction is true when both sentences are true. So they just inverse these two. And instead of the relatively pseudo-complementation, the implication, we have the so-called pseudo-difference. Yeah. So conjunction and disjunction interchanges. In the place of implication, we get pseudo-difference. But this is a delicate issue about the implication in the co-toposes. They say about it a little, but I will leave it here. So these are the consequences I already almost said. That, of course, the subobjects remains a Heyting algebra. This is it depends. It doesn't depend on the. This is just the Cartesian closed part. Even without the complement classifier or the subobject classifier, we have this Heyting algebra structure here. But then, as I said, this would changes the order and becomes the co-Heyting algebra. The distinguished arrow by the complement classifier axiom is now the lowest element of this algebra. And then, if we define some evaluations on a topos of sentences of logic, of language, then we get, for example, I will just skip it, that, okay, in a standard topos, this is true always, okay? But then, if something is, if not something is true, then in intuitionistic logic, the sentence itself is false, not the other way, but this is the way it works. So then, if we get other valuations and the conjunction is reversed by the disjunction, they get, for example, that for these valuations on the co-Heyting, let's say, algebras, we get a principle of excluded middle, which is not present in general in toposes. So very shortly, I'm always done with it, as you saw already, I think. But I think first we have to ask, is the labeling or interpretation of eta a generic subobject distinguished by the Ω-axiom as true as we do in standard toposes, an important and non-removable part of the Ω-axiom? So this is the standard definition. So can we just say here, we don't need this word true. We can just say that subobject classifier is an object together with certain arrow, a global element of omega, such that for every monic we have characteristic morphisms. I think the answer is no, meaning that this is not an important and non-removable part, so we can omit this true. We can just have this definition of subobject classifier. Otherwise, in the very definition of a topos of a complement of a classifier, subobject classifier, we would use a new external and additional notion of the truth, if that would be important and needed. That's not the case, I think, and the name true, why we name this generic subobject true, I think it should result from further analysis of the properties of this arrow. I will say about it a few words later. And of course, the same applies, I think, to the false in the definition of the complement classifier. If not, that would also disqualify, I think, this definition. And now I just give it side by side. These are exactly the same definitions, just they give different names for the same arrows, because an arrow is determined by the condition it fulfills and not the label we give it, of course. So these are just exactly the same definition as I think. And they, I think, do it too easy. for example, this sentence in one work, this about the subobject classifier definition and treating omega as a truth value object, that in this ingenious construction cries out for topological dualization. To dualize, simply rename true with false and relabel the classifier R with the complement classifier. So I don't think that's the way we should do it. And when I was thinking about this all, I have some further remarks. So first of all, this distinguished arrow have a codomain omega. So this is already a characteristic arrow for some subobject of its domain, being an identity of the terminal object. So, and furthermore, there's a theorem, the internal version of the fact that subobjects of any object in any topos is always a Heyting algebra. The internal version of it, this is for example, in MacLean and Merdick, that for any object in any topos, the power set of a power object, is an internal Heyting algebra. And of course, omega is just power object of one. So I think this is the main point for the argument for eta being true. But yeah, if anyone has comments about it, exactly why, because I think this is if we do it in a different way, if this would be not true, then this, let's say, external part, so like the global elements of omega, making not a Heyting algebra, but a co-Heyting algebra, would be somehow not natural or the wrong way to do it, because we know internally this is a Heyting algebra, and what really matters in category theory is the internal structure. These examples with set 0, 1, this is not natural somehow. Yeah, but I will say a few words more about this interpretation, because one could say, instead of the omega axiom with this word truth, let's say, we could just require that the functor sub is representable. Okay? That means that if sub is representable, that means that there's a natural isomorphism between some home functor and the sub functor, and omega being its representing object. And we have a certain, and the Yoneda lemma gives us that the whole set of natural transformations in general between this functor and this functor is, there's an equivalence, isomorphism with the set, this lies already in set, of sub taken on the object here, which we have from the home functor. Okay? So every natural transformation alpha, this, from this functor to sub, is completely determined by an element of this, because we have this equivalence. And we know, of course, that we have to look for how it works for the identity. This is the Yoneda lemma. Yeah, we have how to obtain the whole working of this natural transformation from just this object, of course. And looking for how alpha is constructed from this is exactly what means by having an omega axiom, that saying that this global element of omega is the generic subobject, so meaning that every mnemonic can be taken by pulling back this generic subobject through pulling back through some unique characteristic morphism. Okay, so let me repeat. Any subobject of omega, for any subobject of omega, we get the natural transformation this from home functor to sub. And we can show that for natural isomorphism, this is here are in general natural transformations here in general. But if you have here a natural isomorphism, it can be shown that this subobject is a global element, not any mnemonic. But there is a possibility in general, in general that more than one global element of omega can give rise to a natural isomorphism also. So we have one-to-one correspondence between characteristic morphisms and subobjects, making each of these global elements a generic subobject. So then we would have more, let's say, subobject classifiers. Not only because of the up to isomorphism definition, because of course every subobject classifier is defined only up to isomorphism. So I already showed you the example of set. This is somehow not natural example because we have this external viewpoint from the set theory, and this this object, subobject of omega, which is now 2, we can take any of the elements. It has 2 global elements, and any of them we can take, and we get these 2 ways of connecting characteristic morphism with subobjects. And if we look at the same example as a very special naive example of the pre-sheaves for the category just with one object and one arrow, identity arrow, then of course the omega is the set of all sheaves, and the 2 element is just the empty sheaf and the maximal sheaf. And then the truth arrow takes the maximal sheaf, so it takes a global object of omega. So this is, for me, a bit striking, because this approach gives us just one subobject classifier. And this approach gives us 2, let's say. Of course, they are, I think, isomorphic, yeah? It's Boolean.
That's why.
Okay.
So the opposite of the hanging algebra is the hanging algebra.
Yeah. But if I wanted to see this set as a special example of pre-sheaves, how could I get this second subobject classifier, let's say?
Classify the complements of the subobjects in Boolean algebra that correspond to subobjects. But in Heyting, they don't.
Okay, let's leave it maybe to the end, but okay. Very similar examples are with the product of set, or the set with 2 with an arrow, because we have also the external point of view from set theory, and we can give different subobject classifiers. So yeah, so this is what I already said. Are there many subobject classifiers, for example, for the pre-sheaves or the maximal sheaf is the only one up to isomorphism? Because, maybe let me repeat it, we have this, now we are in the pre-sheaf. So omega is already a functor from C to set, and now the natural transformations from this to this are isomorphic to this set, and different elements of this set gives us different bijections, let's say, between homomorphisms and omega. So it seems like maybe, in principle, this could have different values, let's say, take different elements, and maybe not only one would be connected with an isomorphic, natural isomorphism, not natural transformation.
Well, if C is a discrete category, you can reverse any of the factors you want. Your subobject classifier becomes a product of just the 2 element subobject, and you can reverse any ones you want.
Mm-hmm. Okay, if this is a discrete category,
Yeah.
so just the identity morphisms. But even for this example, the functor category with the category 2 with just one non-identity arrow, this is already not a discrete category. But we have also set with an arrow, and as far as I said, as I checked it from the set theory point of view, we could give other global elements of omega that also classify all the subobjects. Okay, I will ask you later and check it maybe, but okay. Okay, so I just said it because if we think, so this is like a recapitulation. I think the internal structure, for the internal structure, it doesn't matter which we take, if only it really classifies all the monics. Yeah. So for example, if said any 2-element set is a good subobject classifier. And then eta always plays the role of truth. But I was not sure, let's say, what happens if we consider the topos built in already in set theory, where we have this order, and then we see that the bigger subobject, the smaller the characteristic morphism, and we get the co-Heyting algebra. And some concluding remarks. So my objections are only to the above approach to co-toposes or paraconsistent logic in topos theory. I'm not saying there are no places for paraconsistent logic in toposes. On the contrary, I would say, I will show you below. Maybe I was thinking this complement approach could be useful as at least as a non-categorical, let's say, a very unnatural semantical tool for paraconsistent logic. So doing from this external point of view. To be honest, I didn't go through the whole literature, so I don't want to say they are all bad people. Thank you. And one thing I was thinking, because before we add an axiom of a subobject classifier, we have a Cartesian closed category, and Cartesian closed category are already itself connected with Heyting algebras. Yes, because a Heyting algebra is just, roughly speaking, So I thought maybe there's one paper who says that he considered co-toposes different than a co-Cartesian category with a quotient classifier, not a subobject classifier. But I think, yeah, maybe I will not go into it. And another different project would be to search for structures within standard topos theory, naturally exhibiting co-Heyting structure. This is also, so the same James who has this PhD on co-toposes on the first definition, with the first definition, he also is saying about this. So, and he says there are other logic objects within categories that exhibit paraconsistent algebras. For example, I didn't check it, but he says that sheaves over the closed sets of a topological space. And actually, there's a whole bunch of toposes that have co-Heyting structure of subobjects as bi-Heyting. Laville has a work pointing out that any pre-sheaf topos is bi-Heyting, and more generally, an essential subtopos of it is a pre-sheaf. And there's a paper 5 years later with Reyes and Zolfogari. They proved this and introduced a new approach to model operators based on the existence of the two negations, because we have negation from the Heyting and co-Heyting structure. And yesterday, Colin, thank you for that, said me that in the category of toposes, there are some traces of paraconsistent nature. So you said something like this, that there are toposes that has a common, let's say, edge somehow, and the one sentence can be true in one topos and not negation of it in another. So there will be some kind of contradiction inside this.
It's not entirely false. Its support is not.
Yeah, and its support is not empty, but of course it doesn't expand the whole space. So this is a trace of paraconsistent nature, I would say. I have to finish? Yeah. So thank you very much.